So what I'm going to do, I'm going to take you through a design. We'll build a rocket on the screen using the software and fly the simulation. Right, now, I've never done a talk quite in this format before. I hope it goes okay. I'll just point out I'm actually using 2 computers and 4 screens at my end. So I'm hoping that it'll all come together and I get the right screens at the right times. Okay, so let's have a look at OpenRocket first of all. If you've had any experience with programs like Rocksim, this will look very familiar. So a lot of components along the top that you select, dimension, put them together, choose your materials, and then we choose the motors later on and we can fly it. The purpose of today's exercise is to build a rocket that will go to break through the von Karman line. Now the von Karman line is an imaginary altitude, it's a real altitude, an imaginary line at 100 kilometers high. It's the point at which you can no longer use aerodynamic controls at below orbital speed. So effectively, anything above that, you're in space. Anything below that, and you can use aerodynamics to control surfaces to fly your rocket. So the first thing we need to do is see how fast we need to be going. And to do that, we're going to do a couple of simple calculations. Back to there. We'll do a few calculations first of all to see how fast we're going to go. So you should be able to see on the screen. If you're familiar with MathCAD, any of you, but it's a computation program. It's very easy to use, and it allows you to actually see your maths that you're doing. It's got lots of tools in it. I hate spreadsheets, so I tend to use this most things. So the first step is to calculate the velocity required to reach 1,000 meters, 1,000 kilometers, 100 kilometers, sorry. Calc velocity to reach. And we'll do that using the constant velocity equations, v squared equals u squared plus 2 times acceleration times the distance. Okay, sure you're all familiar with that equation. So that's the velocity that we get to is equal to the initial velocity plus twice the acceleration times the distance it's acting over. Right, so the initial velocity is what we're trying to find out. The final velocity is when it drops to 0. So we'll set u equals 0 meters per second. The acceleration is just g, and the distance we want to act over is equal to 100 kilometers. One of the nice things in MathCAD is you're allowed to completely mix your units, and it converts all the units for you and works. So for instance, I could put that in as at 60 miles if I wanted to, and everything would be the same. Right, so we need to solve that now for v. That's not very difficult. It's even easier if you've got a button to press. And now we can just say equals. Oh, sorry. So that's how fast we need to be going at launch to actually get us through the to 100 kilometers high. Okay, 1,400 meters per second. So the next step is to calculate how much propellant we'll need. For that, we're going to use Szyszkowski's equation, which I expect you're familiar with. Again, it's a very well-known equation. Sometimes it's just called the rocket equation. Szyszkowski, as I'm sure you know, was a Russian theoretical rocket scientist around about the turn of the century. Had he been a Westerner, he would have been up there with Newton and the great scientists of our age. But because he was Russian, he's largely ignored, and particularly by the Americans, so they don't even recognize it's his equation, they just call it the rocket equation. Right, so this tells us that delta V, the change in velocity, is equal to SI, the specific impulse, times the log of the initial mass over the final mass. So the initial mass is the mass of the vehicle when you press the button on the launch pad, and the final mass is effectively the initial mass minus what you burned in propellant. So we need to get some numbers in this, and we'll expand this up now. What we're trying to find out, we'll start off with the mass of the payload, and we're going to have a payload of 12.5 kilos. Mark originally asked me to look at this with a payload of between 10 and 15 kilos, and so we went for 12.5. Other bits and pieces that I haven't thought about, there's always extra bits that you don't think about, glue, fixings, bolts, rivets, the rest of it. I'm going to call these extras, and I'm going to give that 2 kilos. The specific impulse, again, you may have different units for specific impulse, but there is only really one sensible unit. The specific impulse is the amount of impulse you get, that's the number of Newton seconds you get for every kilogram of propellant. I know a lot of people would use seconds as a unit of a specific impulse, but it's a silly unit, really. The correct units are Newton seconds per kilogram. Newton seconds per kilogram. The delta V that I'm looking for is, as we set up here, 1400 meters per second. So now we have to express this equation in a slightly longer form, and we need to express the motor mass in terms of the propellant mass. So I'm going to say it's quite a reasonably high performance motor, and we're going to say that the motor is, just the rocket motor itself, is 80% propellant. So it's got a mass fraction of 0.8. So we'll say mass fraction equals 0.8. So 80% of the rocket mass is propellant. Right, so let's express this equation now a little bit bigger. So delta V equals the SI times the log of the initial mass. The initial mass is the mass of the payload plus the mass of the extras plus the mass of the propellant plus the mass of the inert bits in the rocket motor. So that is the mass of the propellant divided by 0.8 minus the mass of the propellant. Okay? So that's what it is at takeoff. After the propellant has burned, it's everything in here except for the mass of propellant. So we'll just copy that down. Take out the mass of propellant. Right. So we now got the initial mass divided by the final mass. So we need to solve this now for propellant mass, because that's what we're trying to find out. That's quite a difficult thing to solve. So I'm going to invoke the magic of MathCAD again and just say, solve it for me. Thinking about it for a moment, and I think I must have a mistake in there somewhere. Oh, sorry, I put a number in there. I'm just going to go back and make those a constant.
Ian, sorry to interrupt. We've had someone drop out, and you're in control. Are you able to let them in? On participants.
See waiting room.
Yep.
One person is waiting.
Yep.
Admit.
Fantastic. Thank you.
Okay. Right, so we'll solve that again. As I say, we're just trying to find out, rearrange the equation in terms of propellant mass. So that should look like, okay, that looks better. Because it's quite a tricky little thing to solve there with these log functions to evaluate. So if we solve that then, and that's telling us, evaluate that, so that's telling us we need about 12.5 kilos of propellant in the rocket to get there, which doesn't actually sound a great deal. And I wanted to go through that calculation first, just to show you that you can't actually, there's no shortcuts to doing this, and to demonstrate the shortcomings of doing it empirically in this way. But we just need to confirm those figures now. So I'm just going to change my screen. Okay, and we'll just nip back and have a look at another little program, this one. So this is a little calculator that's on the NASA website, which is quite useful. And we're going to just plug the numbers in that we just calculated into here and see what it tells us. So the first thing is we're going to be working on Earth. And in this case, first of all, we're going to ignore drag. We're going to set the units to metric. Now the initial velocity we said was 1,400 meters per second. We don't need to fill this in at the moment, but we will just anyway. So about 45 kilos. Cross-sectional area is 0.031415. Drag coefficient and altitude. Right, so that's telling us 1,400 meters per second will take us to 99,851 meters. So we were right. You know, we thought that would take us to 10,000, but 1,400 is, if I express that to the right number of decimal places, I'm sure we'll get an exact fit. So that all looks good. However, we've got this ignore drag. If I now include drag, you can see the maximum height has now dropped from 100,000 meters to just under 7,000 meters. So that's the effect that the drag has. So you can't just go and jump in to do these calculations straight off. In fact, it's actually even worse than that, because with that amount of propellant, with the atmospheric drag, we wouldn't get to 1,400 meters per second anyway. So it's worse than it sounds. Okay, so let's see what we've actually got to do. So now I need just to switch to another screen, which is this one. So back to Open Rocket. Well, the rocket we're going to build is 200 millimeters diameter. There's no real reason for that. It just seemed to be a nice sort of shape to work with. I'm going to do this now by selecting components and installing them. Right, we just pick up the pieces one by one. So a nose cone. The shape of the nose cone is an ogive. If you're not familiar with what an ogive is, it's a cone with a circular arc for the side. And I can explain that by, that's a conical nozzle, a conical nose cone. And if I replace this with a curve, and if the center of the curve is on this point along this line here, then it will blend continuously with the motor body. So let's put that to an ogive. I can adjust the shape of that as well just by dragging that slider up and down. I'm going to set the cone length to be 300 0.3 meters. And I'm going to set the base diameter as 0.2 meters. That might look a little bit short and fat, so let's make it a bit longer. There we go. That looks a bit better. The wall thickness we'll leave at 0.002. Materials, we've got all these different materials we can use, and these are used in the mass calculations. Lots of materials built in. We're going to use carbon fibre. We can choose a paint finish. We'll go to smooth paint. And we'll go to appearance. And I'm just going to change the colour, just so we can see the components more clearly later on. These are just random colours really, but each component now will be given a different colour. We've got a shoulder on it, so it interfaces with the next one. The diameter of the shoulder, we'll say, is 0.196, 2 millimeter wall thickness. We'll set a length of it to be, I don't know, 0.2. Okay. That's going to be 0.002. So we just got an interface now for the next section. Close. And what I should have done just before that is set a few things up, which you will need to do if you use this program. Let's just go to Edit and Preferences. I think you will have had a list, a download of a series of motor files, different motor designs you can play with. You'll need to unpack those and stick them somewhere where you know where they are, and then go to User-Defined Curves under the General and Preferences, and click Add, and then find the folder that you put them into and add it. So it's just so the program knows where to look for the files. You can also ought to go to Units, select Default Metric. That way it'll all work properly. And I've got my dimensions in meters, where I think it probably will come up in millimeters if you just do it otherwise, but that's fine, whatever suits you. Launch, we want to set the average wind speed to 0. Standard deviation, this is just to give variability and turbulence in the upper atmosphere. We can set these things. We want to make sure that the International Standard Atmosphere box is ticked, otherwise you can have to put in your own atmosphere. The launch site is a little bit irrelevant, but those are the coordinates of my house, so we'll launch it from my garden. The launch rod is effectively, for us, it's the launch tower. It's the height, it's the length over which the rocket flight is constrained while it's going slowly. Always launch directly upwind or downwind, where you can tick that if you want to, but because we've got 0 wind, it isn't actually going to do anything. And the direction, the box comes up to remind you, is the direction of the launch tower, which we will say is 90 degrees. That's vertical. This is the direction of the launch. Sorry, the angle there is the direction of the launch rod from the vertical, so it's 0 degrees. So it's straight up, 0 degrees off the vertical. That's the wind direction at 90 degrees, but as we've got no wind, it doesn't actually do anything. Okay. Well, the next component we're going to install is the payload bay. That's a body tube. So we'll select that. And we're going to set the length of the body tube to being 0.3. The outer diameter gets filled in automatically from the previous section because we've got the automatic box ticked. And these again are filled in automatically. We'll change the material again to carbon fibre. And we're going to change the appearance. We'll just have another colour. We'll have a pink. Okay. You'll see if I change the viewpoint now to 3D finished, you'll start to see what it's starting to look like. Just before we leave that, when I bring that one back up, I'm going to change the component name from body tube to payload bay, just so it's easier to keep track of. So we've got the payload bay, we've got the nose cone, And now we're going to put the rocket motor body in. Now, with this program is intended to be used for model rockets, and the way that model rockets are normally built is to have a tube in, and you put the rocket motor inside the tube. Real space rockets use the rocket motor body as the tube itself. So it doesn't go inside anything else, it's actually part of the structure. However, we need to have a tube here to make the program work. So we'll fiddle it slightly. We'll put a second tube in. And we're going to make this one, oh, sorry. We're going to call this motor tube. It's going to have a length of 1.25 meters. The diameter, I'm going to set slightly bigger than that. And the thickness now becomes 1 millimeter. That's done automatically. So what I'm going to do now, I've given it 1 millimeter wall thickness. We'll keep it as carbon fiber. But we're going to trick the program into actually not assigning any mass to it, because the mass is already included in the motor design itself. As I say, so this is not a real component, it's just there, it's a virtual component just there to make the program go together as it's supposed to do. Well, I do that by clicking the override button, and I'm going to override the mass and set the mass to 0. Because the mass for that component is already included in the mass of the motor. And the other thing we have to do is to say this is the motor mount. This is the part of the vehicle that the rocket motor is attached to. So this is where the motor is fitted. Okay, and this motor will be ignited automatically at launch. You can change that to different things if you want to. Okay, so it's still coming along. Did I put a colour on it? Appearance. Right, now we need some fins. The purpose of the fins is to provide stability. To do that, we have to look, the program has to calculate where the center of gravity of the rocket is and where the center of pressure is. I'll just explain the center of pressure in a moment. I'm sure you're all familiar with the center of gravity. So I'm just bringing up my crib sheet. So on this one here, now we have to add some fins. There are various fins we can choose: trapezoidal, elliptical, or completely freeform. Well, we'll just go for the trapezoidal ones because that's easy to put in. And straight away, it's put some default ones in, you can see, which are not a lot good, really. I'm going to go for 4 fins, just because it makes some of the other calculations easier. The fin rotation and the fin cant we won't talk about for the moment. We'll come back to those perhaps later. The root chord, that's the width, or the length of the fin along the base, is going to be 0.030 centimeters. If I click there, and the tip chord should be the same. Why does that come out? Sorry, 0.3, not 0.03. Okay, so now we've got some fins appearing at the back and sensible sort of length, and we need to make them higher. We're going to make them 0.15 high, 150 millimeters high. Okay, so that's starting to look better. It'd be quite nice to have some swept fins, so we're going to make them 0.2. So I look like a proper rocket now. it's calculated a sweep angle of 53.1. You can set either of those and it calculates the other one. And we can set the position relative to the parent component. So I can actually move them up and down, as you can see, through the body. We'll leave them like that for the moment. Right, so we've got a basic outline now. Now what we need to do is to stick a rocket motor into it and see what it looks like. Then we can work out the centre of gravity and the centre of pressure. So have a quick look at it first. Why is it doing that? I'm not quite sure. We seem to have got a number probably in here incorrectly. I don't know quite what it is. What I'm going to do is jump to one I prepared it earlier, which won't have that error in it. Clearly, we put a number in wrong here, and it's or the program's gone into a little bit of a bug. So I'm just going to bring up exactly the same rocket, same model, but with a different version. What I put into it on this one also, in the payload bay, we need to put a payload in. We do that by adding a mass object. So here, we can just add a lump of something, and we're adding in a mass object. We called it a payload. You can call it anything. We've given it a mass of 12.5 kilograms, and then just bulk the shape out to make it look roughly right. It doesn't. These numbers don't really mean anything. Right, now we have to look at some motors. So we go to Motors and Configuration, New Configuration, Select Motor. Now when you open this, you'll find that you've got hundreds of motors here from all these different manufacturers. These are all model rocket motors, and there'll be hundreds of them in there, all in the database. Now that's just too confusing, so we'll clear all of that, and we will just select BISWM. And these are a set of files that I've created to explain as examples for this demonstration. Don't go away thinking these are real rocket motors. They're just created by an algorithm. There's no guarantee any of them could actually be made. I mean, they're all sort of realistic based on sort of real numbers, but whether you can actually achieve any one individually is a moot point. Right. So let's go down and pick up one of these motors. Let's start with 1A. There we are, motor 1A. Have a look at the details of that. What I've done, I've given you a boost sustain profile with a 10:1 ratio between the boost thrust and the sustain thrust. It's about 47 kilonewtons of thrust of impulse, kilonewton seconds of impulse. It burns for a total of 16 and a half seconds. It's 24 kilos and a bit at launch, and it's 4.8 kilos at the end of burn. These are all just based on sort of typical ratios. Okay, so there's the motor in place now. And now we've got the motor in place, we can start looking at the stability, because that's how it's all affected. Now you know, I'm sure you all know what the centre of gravity is. It's just simple here. So if we were to tie that rocket to a piece of string, it would balance at that point. Equally important is the centre of pressure. And that's the point at which, similar to the centre of gravity, but all the aerodynamic forces are balanced. And the way you can think of that, and a way on model rockets you can test it, is what's called a cardboard cutout model. So if you were to take this design here, lay it out on a piece of cardboard, and just cut it out so you've got a flat model. And then you could take the flat model, and if you tied a piece of string to that and balanced it, the point at which it would balance would be the centre of pressure. So it takes into account all these extra dimensions, all these extra bits here. So effectively the area times distance of all of these bits behind that point is the same as it is in front of that point. And the rocket it's like, think of a dart. You know, when you play darts in a pub, the fins are at the back, you have the weight at the front, so it's very, very stable. If you try and throw it backwards, like I'm sure we've all done, it just turns around in flight. So the fins slow the front down, turns it around, and it will go and point forwards. If that motor was thrusting when that happened, as it turned around, the thrust would be in at a vector going at different angles, and it would tumble and fall out of the sky. And I'll show you that in a minute. So for a stable rocket, we have to have the center of gravity at least one caliber, one rocket motor diameter, in front of the center of pressure. And that's called the static margin. And that's this figure here. At the moment, we've got 1.2 calibers. Now, the propellant burns away during the flight, so this gets lighter at this end, so the center of gravity moves forward, so it gets more stable as the flight carries on. If you don't have this caliber, at least one caliber static margin here, it will crash out of the sky. Right, so we selected our motor, and it's a BIS 1A motor, and now we'll go to flight simulations. Simulate.
Ian, can you hear? Sorry, the screen's just updated. It was showing the old rocket for quite a considerable time there. But it looks like it's just updated for some reason. So I'll shut up and leave you in peace.
Do you want me to go back and do it again, or?
I'm okay.
Okay. So can you see my mouse moving around?
Yes, can now. Yes.
Oh, okay.
It was stuck on the original rocket with the problem for quite a while. As soon as you brought this up, it's updated the screen for some. I don't know quite what happened.
Okay. Well, I hope you can stay with me on this. We're now on the simulation screen. This screen contains the information that we put in at the beginning, the wind speed. It always changes the average wind speed to 0.1. You can change it back to 0, but next time you look at the screen, it will be back at 0.1. Doesn't like 0. These all figures 0, standard atmosphere. So this is just a bit of fun. Launch rod 5 meters, and simulate and plot. So it's done the calculations and draw the graph. Right. On this particular graph, you can have a wealth of different graphs, but we'll come to those in just a moment. The red line is the altitude. So it's taking us up to a maximum altitude of, what, 23,000 meters. Bearing in mind we're looking for 100,000, we're a long way off. The green line is acceleration. So we've got a high acceleration when the motor was at high thrust, drops down after a second, and then carries on the low thrust, acceleration gradually increasing. Motor burns out, acceleration drops, and then continues. And acceleration gradually increases as we pass the apogee, because now we're coming back down again under gravity. This little bit here, I can just zoom in on that, can I? Won't play. The acceleration increases even though the thrust is constant, because the motor mass is dropping. As we're burning propellant, the mass of the vehicle is decreasing, the thrust is the same, and F equals ma, so acceleration is increasing. So we would expect acceleration to be increasing there. Right. So we clearly need a bigger, more powerful motor. Just close that. There's a whole load of other graphs we can look at, some built-in ones. Or if you want to, you can set your own ones up. So if we have the x-axis, I don't know, we'll leave that at time, and the altitude, the y-axis at vertical velocity. There we go. So you get a load of information you can get out of that. And you can also, if you want to, create a data file, if you want to take that out and do that something else elsewhere with it, and select which attributes you want in the data file. Right, so that motor's not good enough. Okay, this little corner down here gives you an instant readout, more or less, of what's actually going on. So it's telling me we're getting 24,000 meters, we're getting 792 meters per second, and the maximum acceleration is 519 meters per second squared. Well, that's about 50 G. That's quite high. I would like a lower figure. You know, it's good to get below about 30 G, I think, this sort of thing. What we can do though now, let's just look at changing a couple of things. Let's bring the nose cone back up. Let's change the shape of the nose cone. And you can see in the bottom left-hand corner, can you, that I've made the nose cone more pointy, and the apogee now has dropped to 13,000 meters. So you can do all sorts of little optimization things there. If we look at the fins, we've got an aerofoil section here. We could have square fins if you wanted a nice easy one. If I make 24,094 meters, if I change it to square fins, it drops to 21,000. So just putting an aerofoil profile on the fins gives us an extra 3,000 meters in this case. So you can just fiddle around there and just see what happens. Right, let's put a bigger motor in. So select motor. We'll go a B4A. The B1 was 48,000 Newton seconds. Let's go for a B4A, which is the same sort of profile, but it's 77,000. It's almost double the impulse. Okay? So we've now got the same thrust in boost, but the rest of the impulse is taken in the same thrust in sustain as well, but it goes on much longer to use up the rest of the impulse. So we've got 31 seconds now instead of 16 seconds before. So it's grown in length, and straight away it's jumped up to tell me we've got 69,000 meters now. Let's have a quick look at the simulation. I'll just set that back to the vertical motion as the standard graph. Again, you can see acceleration increases throughout the sustained phase for 30 seconds. That's our acceleration is, maximum acceleration is about 400 meters per second, so that's dropped a bit. And that's not surprising because the thrust has stayed the same, but the mass has increased. So just remember that number there, 69,710, and we'll just try a different motor. Now that was a 4A. Now if we do the 4B motor, it's just about the same total impulse, but it has more time in thrust. It's more time in the boost phase. Instead of 1 second, it's got 2 seconds. So if you look at this graph, we've got a short boost there and a long sustain. If I go to 4B, we've got a longer boost and a shorter sustain, but the total area is about the same. So that took us, I've forgotten what the other one was. We're at 65,000 meters now. Let's just go back to the 4A. And that's 69,000. So going, even though the impulse is the same, we're burning more propellant at low altitude, where the air is denser. So it's going faster in the thicker air. So we've got more losses due to aerodynamic drag, because drag is proportional. Got some more people in the waiting room, I'll let them in. The drag is proportional to the velocity squared. So the fact it's going faster in the denser air means that it's actually going to be, we're losing more to drag, so it's not such an efficient system. We actually want to burn most of our propellant, to deliver most of our thrust where the air is thinnest, where drag is lowest. But on the other hand, it's got to be going fast enough at low altitude, off the launch rail, for the fins to be going, providing stability. And I would take that one step further. If I go to a new motor again, that was 4B. If I go to 4I, I think, yeah, so 4J. 4J. So 4J is more or less all boost. It's 1 3/4 seconds. It's 1 3/4 seconds, and it's high thrust, 50 odd thousand newtons, 73 kilonewtons altogether. So it's actually slightly less thrust, it's like it's impulse than the previous one, but we've got about the same, bit less energy. And now look, the velocity, the altitude has dropped to 27,000 meters. So by putting that in, same amount of energy, but burning it all in 1 3/4 seconds instead of burning it all over 35 seconds means that we don't get anything like so high. All that drag's built up in the low altitude. Right, one last motor. Let's go into the 5s, and we'll look at 5A. This is a 90,000 Newton motor, Newton second motor. 1 second boost again at 20,000, so that's the same as the previous A ones we did. And now it just burns on and on and on, what, 36 seconds in low thrust to give me a long duration burn. So all the rest of it, but the area is more or less the same. That's grown a bit longer again, you can see. And now that's taking us to 99,748 meters. So we're just about there, just about on the Karman line. So if you actually want to get over the line, what can we do? Well, let's have a look. Let's just take a little bit of payload out. We'll bring that down to 12 kilos. There we are. Now we've got 102,000 meters. So that motor should launch our rocket to about 102, 103,000 meters. But we busted the von Karman line according to the model. Now, what I said earlier on about the stability, what we have to make sure is that we don't, these two numbers don't approach each other by closer than 1 caliber. So how I'm going to do that is by moving the center of gravity aft. And I'm going to do that by taking mass out of the payload. So if I reduce the payload from 12 kilograms to, I don't know, 1 kilogram, you can see that the center of gravity now is very close to the center of pressure. We've only got a static margin of 0.37. So we would expect this to be unstable. And you can see immediately what's happened to the altitude. We dropped from 102, even though it's 10 kilos lighter, we've dropped from 102,000 meters to 10,000 meters. Let's just see that on the simulation. Well, first of all, you can see we've got a very noisy plot. The vertical acceleration is all over the place. The vertical velocity is all over the place. And if we now look at the stability versus time, so we've got the margin in calibers and the locations. Let's just look at that. And you can see it's completely unstable. The stability margin is all over it's gone. The center of pressure is but the whole thing is just tumbling out of the sky. So it's not going anywhere. So even though we took 10 kilos out of the mass, we've taken it in the wrong place and it won't go as high. Finally, if I let the mouse hover over these simulations, it gives you a little bit of extra information. It says large angle of attack has been encountered, so more than 180 degrees, so it's tumbling. Stage begins to tumble under thrust. The first one is quite interesting. Body calculations may not be entirely accurate at supersonic speeds. They're not bad, but this vehicle's going to Mach 2.5 in this configuration. I think it was significantly higher than that earlier. What you can do to get a better model at this point is switch to another program which is similar in many ways, a program called RAS Aero 2. That's RAS Aero 2. RAS Aero 2 is a similar program. You build the rocket from components. You've got more components, and you've got more ways. For instance, on the fins, you've only got 3 options on this one: square, rounded, or aerofoil. Well, you've got about 10 on RAS Aero 2. But what it doesn't do is give you the center of gravity position. That doesn't give you a mass calculation. So what you need to do is to build your vehicle in OpenRocket, and under File, you can export it as a ROCSIM file. You can save it as an open rocket file or as a ROCSIM design. And if you save it as a ROCSIM design, you can import that directly into RAS-02. And that's a better supersonic model, and it also comes with all the, it's fully calibrated, and it gives you examples when you download it, how it's been validated against proper sounding rockets. Okay, I'll just stick the payload back to what we wanted it to be. So it's 12,000, and we can see straight away in the bottom left-hand corner, it's recalculating and gone to 102,000. If you want to, you can add a recovery system. There's various ones built in. You can have a streamer or a parachute. If you are messing around with this, I would put a parachute in for a moment, see what the mass of it is, and then take it out again. And I'll show you why. If I put a parachute in, it does the calculations for you, gives you a suggested diameter. It's actually right at the top of the nose cone at the moment, but just if I now run that as a flight simulation, I did it quite quickly that time, but very often it will take an awfully long while to do the calculations for the parachute descent. So you don't actually need the parachute in there for your calculations. You can have various other recovery systems if you want them. I'll just take that out again. Okay, I think that's just about it. I think the basic thing is, don't forget, you can do your basic calculations and see how fast you need to be going to get the altitude you need. But if you're on a planet with an atmosphere, that won't work. So really, and it depends heavily on the thrust profile you're using. You can have if you have a very short burn, very high thrust, you'll be nothing like as efficient as you would be if you're burning your propellant and providing your high velocities at high altitude. What you can do next, if you wanted to, is you can add another stage on here and make it into a two-stage rocket. And you can go on putting as many stages in as you want and tracking the center of gravity and so on. Fine, just on this one, you can see we've got a maximum acceleration of 358 meters per second, or 35 G. That's okay. And we're getting up to Mach 4. So it's going, it's pretty smoky. It's going quite quickly to get there. And it looks about right, doesn't it? When you look at the shape of it, yeah, it looks sort of about the right proportions. That's why I coloured each piece differently, so you can see what they all are now. Okay. Right. Well, if anybody wants to have a go at doing something now, I'll stick around for the next hour or so, and you can load the software, you can load the motor files and have a play, and I'll be here to help you through it. If I hand, Bob, you want to take back control now?
Yes.
Thank you very much, Ian. While Bob takes, if Bob takes back control, what we'll do is we'll open for questions. Just to say that obviously this is Ian's produced a design which is based on the brief that I gave him. Now this is a non-optimized design. I just asked for a single stage just to make it easy to do. Things like the real sounding rockets that around the world normally have a booster stage and a sustainer stage. So the boost stage fires, gets the thing up to speed, so it will fly aerodynamically stable. That drops off, and then the second stage burns along low thrust to altitude. The disadvantage with the thing we've modeled here is because it's got, the motors have a very high boost and then a long low thrust sustain, you have to design the rocket motor to take the high pressure of the boost section. So it means you're carrying a lot of additional high strength components, mass. So this is not an optimized design. With that, open to questions. And thank you again, Ian. That was great.
Okay.
Any questions?
I have one, if I may.
By all
Yep.
means, Griff.
Hi. Oh, hi, everybody, by the way. Greetings from down south. Hi, Steve. Another one, another Londoner. Good show. When I tried playing around with when I downloaded OpenRocket, the only buttons for components that were in black, if you see what I mean, the others were ghosted, were nose cone, body, and transition. Now, I was able to model a boat tail by making the transition the wrong way round, if you see what I mean.
Yeah.
Smaller at the aft end than the forward end. But it wouldn't let me put fins on the thing.
Okay.
They ghosted.
You can only put fins on a body tube. So you select the body tube, put it into your model, and then the fin icons will come up.
Oh, I get you. No, so you can model a boat tail in this.
Well, you can put a transition backwards on a boat tail, but you wouldn't be able to put fins on it.
Oh, I get it. Okay.
You can only fins are a sub component of a body tube.
Oh, I get you. So something like the V2, which had its fins on the boat tail, wouldn't be simulatable in this.
I think you would struggle.
Okay.
It is intended as being a tool for model rocket people.
Okay.
But what I just have I got control? Can I share this?
You're still muted, Bob.
Yeah.
Yeah, can you give me that sharing rights, Bob?
There you go. You got it now.
Thank you. This is another one. This is the same rocket we've just designed, but with a big first stage on it as well. So you can just carry on combining sections and have as many stages as you want. Oops. Is that, oh, what did I do then? So now we've got stage 1 and we've got the stage 2. We've got 2 sets here. We've got the sustain phase and we've got the booster phase. And again, as we just said, you can only put the fins onto a motor section, onto a body tube. So there it is. And if we fly that, yeah, I think perhaps the model wasn't complete there. I've got no payload in it. And we see we've got a much bigger motor there. And the whole thing now has gone up to the 1/4 of a ton. It's quite a serious vehicle. Okay. Any more questions?
But it occurs to me that since Skyrora put the motor they were using in their Skylark Nano sounding rocket that they launched from Shetland last weekend on their website, it was a Cicerone something or other. Did I pronounce that right, Steve? It should be possible to simulate their rocket on this.
Yeah, I'd have thought it would be. Do you know what motor it was?
One moment while I try to figure out how to get out of this and into something else. And wait a minute. First launch from Scotland.
The motor used is a standard hobby rocket motor. It's a relatively low performance
Yeah,
toy rocket. It's perfectly acceptable as a toy rocket, a hobby rocket.
it's an M1520BS.
Well, the database, I can call that up. It's that's a 24 millimeter motor though. That's very small. Oh, hang on, maybe not. Sorry. So tell me again what designation was.
M1520BS.
M class is going to be about a 98.
Well, I've got
About a 9800 mil diameter.
yeah. The vehicle's 0.102 meters diameter, 2 meters length. I've got thrust average and maximum thrust figures here, if that helps.
Now I've got them in alphabetical order now. Tell me again what the designation was.
That's Mike-1520 Bravo Sierra.
Okay, I've got that. It's
While Ian's doing that, to give you an idea of the performance difference,
I reckon.
the vehicle that you're describing went to 6 kilometers. A skewer sounding rocket, which is only 25 millimeters bigger in diameter, was capable of going to in fact, that's the payload bay and the nose cone. That would go to over 100 kilometers with a full spec large rocket motor in it.
Okay.
They had a lot of payload, and the specific impulse is quite low in the Cesaronis.
Yes.
Can I have screen sharing back, Bob? Okay. Well, can you see that? Is that there?
Yep.
That's that motor you mentioned, Bob. The BM1520MS. Sorry. Okay.
Yep.
That's what it looks like in our vehicle.
So you could try it in this and see what happens?
I can fly that for you. Well, it doesn't work in our rocket particularly well because let's have a look at what's going on there. It should be stable. It says it's only going to get to 2,600 meters anyway, but this isn't the right vehicle for that motor.
Well, they do have a scale drawing on their website, so given the diameter dimension, it should be possible to...
Absolutely, yeah.
Yeah.
And if you can get the mass right as well, that's the other thing.
Yeah, I think the total mass is on there. Hang on a minute. Mass at liftoff of 13,325 kilos. Oh, was it? Sorry, 13.325. That's better. Payload 1 kilo.
Yeah, 13 kilos, right.
Right, isn't it?
That's quite a heavy bird.
Well, the motor itself is 6.7 kilos. With an empty mass of 3 kilos, so that's only barely a 50%. You know, we're working. It's half of that is inert almost, whereas a good, properly built space rocket would be in excess of 80%.
Well, one thing that'd be interesting. A while back, Rick and I damn near bust Excel by doing a spreadsheet to do this sort of thing. It's available from Rick's website. We can compare one to the other. Fun?
It's purely an exercise, Griff. Yeah.
Yeah. Well, you didn't believe it had worked to begin with.
Well, yeah, that's true. Yeah.
Oh well.
Ian, may I ask, that looks quite a fat bird. Is that the sort of length to diameter ratio you'd expect for such a large sounding rocket? Ones I'm not used to.
It's quite short, isn't it? It just depends how much you want to put in the payload bay.
My experience with admittedly much smaller sounding rockets is that the small ones are particularly susceptible to drag loss.
Yeah.
So we tend to make them ridiculously slender.
You could make that longer if you wanted to, but you're only putting it in the payload bay.
Well,
it has sufficient stability, so it's good enough. I mean, let's see what happens. I could make the payload bay. First of all, I'm going to take that silly motor out and put something in a bit more sensible.
don't forget, Rick, the more slender you make it, the higher you're increasing the ratio of skin friction drag to cross-sectional area drag.
Yeah, but
Oh God, does that mean something?
small rocket motors, or small rocket vehicles really suffer because the cross-sectional area is much larger compared to their internal volume, e.g. mass.
This is why you do lots and lots of modelling. You sort of in real life, not toy rockets. You model it and model it and model it and build up a picture of where you want to go.
Toy rockets.
Sorry, it's what it is. That's what they're sold as.
I was doing some work a while ago for somebody else. For a multi-stage rocket, and it came as quite a surprise to me that there wasn't any proper algorithms for designing a multi-stage rocket. I mean, there's certain rules of thumb, but there isn't an equation you can write down to say how much you need from each stage and when your staging should be. So I actually did a big Monte Carlo simulation to work out the staging strategy I wanted to use. Just looking at this now, everything is the same. I've made the payload bay from 0.3 to, I think it was 1.3, 1.5. 1. Okay, it's up to a meter long, and that's reduced the altitude by 16,000 meters.
Interesting.
And the total mass won't have changed very much, will it?
Well, it just goes to show you, doesn't it? We are just not used to firing such big vehicles, basically.
Yeah. The Mach numbers come down a bit. That's not the same motor we used originally. I'll put that one back in just for comparison. It was a 5A, wasn't it, we used?
Yeah.
Like a bit higher, 86,000. It went to 103,000, was it before?
103 kilometers, something like that, yeah.
Yeah, sorry, 100, yeah. So it's 86 now. So the extra length has actually not done us any favours at all.
That's very interesting.
Yeah. Well, don't forget, as the slenderness ratio increases, the lift generated by the body likewise increases and increases the drag.
Well,
we haven't got much of a static margin now, so we've got a stability issue. We've only got 1.15.
Yeah, my screen is still showing the original. It hasn't updated again, I'm afraid.
Sorry.
I don't know about the rest of you.
Yeah, me too. I've just got a whole lot of questions. In your professional experience, why is it, do you think that toy rockets, as Mark called them, the Cesaronis, have such low performance compared to the kind of things that you guys work on?
Okay, there's several reasons, but many of them are reloadable, which means that the case has to be manufactured much more strongly and with removable enclosures, which will mean screw threads and so on. Often in the model rocket community, they're more interested in spectacle than altitude. So they like sparks, they like smoke, they like flame, which don't actually give you a good performance of the motor.
Mhm.
And they're just not made to the same. I think there's a cost in it as well. I mean, a motor that I was involved in throughout my entire working life was a 30-kilo charge. It was a missile motor, the motor for the Seawolf missile. It was 30 kilos, burned for 2 seconds. It's a ship-launched anti-aircraft missile, anti-missile missile. The charge cost about £12,000, and the case was about the same. So you're talking of between £20,000 and £30,000 a unit. Now the Cesaroni one, I would guess, would be 50. Don't know.
Yeah, 50 to 100, something like that.
Yeah, you get what you pay for. You know, it's
Okay.
it is a different technology.
I'll stick to half A's. It's much.
I'll come in there as well. There's nothing wrong with toy rockets. I'm a big fan of toy rockets. I like flying toy rockets. They're great, but it's an appropriate the rocket motors are an appropriate sophistication for what they're going to be used for. With some of the high performance rocket motors that you get in military and space systems, you wouldn't want amateurs playing with them. They're basically they'd be too dangerous for people in a field without specialist training. And when I say specialist, it's not very specialist, but the disciplines and the training just aren't there, and the safety procedures just aren't there in the hobby rocketry community. And for that reason, you don't get very high performance rocket motors. There is another reason, which Rick and I have discussed in the past, which is Britain, if you have a very high performance rocket motor, Britain used high performance rocket motors in unguided vehicles to shoot down aircraft in the Second World War. And I would suggest that we don't want to, the authorities would not want you being able to aim at things in the air. So that's
what about the guidance
don't
system?
get very high performance rockets. It's a safety issue.
Yeah, that certainly makes a lot of sense. Cesaroni do better quality motors, but as you say, they're military and much higher performance. So.
But just looking at that Cesaroni motor we looked at a moment ago, according to the database, it was only about 50% propellant, whereas most military motors will be in the region of 80%, and apogee motors will be in excess of 90%.
That's a very high mass fraction.
It's phenomenal, yeah. But then they'll be using things like titanium cases and all sorts of exotic materials to keep the mass down. It's just done a different way.
I believe Summerfield used to use wound steel strip cases.
Oh, the Ravens, yeah.
Yeah.
It was steel strip laminate.
Sorry, Ian, I'll let you continue.
Yeah, the Summerfield manufacturing technique was based on steel strip laminate, which is a very high tensile steel in, I think it was 1/4 millimeter thick sheet. It's razor blade steel, which was then wound, it was coated, surface treated, coated with epoxy resin, and then stored in a semi-cured condition. And when you need it, you wind it onto a mandrel, several layers thick, as many layers as you need to get the pressure strength you need. And then that's cured on the mandrel, which makes the glue melt and rebond. And you end up with extremely round, extremely thin, extremely strong tube, which is extremely expensive.
Would you like to say something about the construction of the British sounding rocket motors? Because the guys are confusing the two.
Oh, okay. The steel strip laminate process is akin to a toilet roll, for instance. The center of a toilet roll, where you've got multiple layers of material on top of each other, bonded in place. The old sounding rockets that were made at BAJ at Western Supermare used a technique called helical welding. which I think is probably what Mark's alluding to.
Yeah.
Yeah.
Where you have a short mandrel. The feedstock is of the final thickness, so you only get one layer. It's fed on at an angle to make a spiral, and then continuously welded on the machine as it comes off. So you end up with a very long tube with a spiral weld all the way along. And you cut that off in logs and use that. And that's what Skylark and all the 18-inch series rockets, virtually all the sounding rockets are made like that. It's a very good technique. It makes a very round tube. But for a production technique, it's not that brilliant because you have an awful lot of weld to examine. And all those welds have to be x-rayed, and you've got miles of it. X-rayed and qualified, and you go through and tested. But you do get a very reproducible, very round tube. Another way they used to make them was wrap and weld, where you get a sheet, you wrap it round a mandrel to the top, and then weld along the top, and then weld the end closures on. But it's very difficult to get those round. And for the hobby market, maybe round isn't actually quite so critical, but it is for an airframe. It's got to be completely round because your fittings on the outside, fin carriers and structures have to be precision aligned on jigs. And if you're not perfectly round, it won't work. So motors like Black Cat, that's a Seawolf motor, and I think Hooper was the same. The Skyflash motor were wrapped and welded, and then the end rings would be welded on as well with supports to take the nozzle closure and so on. With a strip laminate motor, because it's bonded, the steel strip laminate, you can't weld onto it. So the end closures have to be bonded in as well. So you end up with a very thin parallel section tube, and you have to bond a ring into the end, and you have to calculate the bond areas and so on to get the strength. And then those provide the attachments for the closures and the blast pipe if there is one, and the nozzle assembly at the other end. So it's a fully bonded structure, strip laminate case. When it was discovered, invented 40 years ago, it was state of the art. It's nothing like it in the world. And it's still the same.
It sounds like almost a prototype filament wound, but using a very thick, flat filament in a way.
Well, it's 100mm wide strip.
That's very wide filament, yeah.
Yeah, and I think it was 1/4 millimeter thick. I'm fairly sure it was.
It's a very good idea, though.
Yeah, it has in a military context, it has various other advantages, because one of the things you don't want in a military environment is if you have a rocket motor that's in a fire, you don't want it to detonate. Now, if you take a normal motor in a monolithic tube, you'll get hotter and hotter and hotter and hotter until the propellant ignites throughout its entire structure simultaneously, and you get an explosion. But because this is bonded together, the glue loses its strength as it gets hot. So it actually ceases to become a pressure vessel before the propellant reaches its ignition temperature. You still get a fire, and you get very vigorous fire, but you don't get an explosion. And even if you do manage to get an explosion, you don't get lumps of metal flying around like you would do in a monolithic case, because it unwraps and you get just thinner sections like you would with a composite case. So it's got a lot of advantages, and it's sort of come back into fashion with the requirement for, it's called insensitive munitions, motors which will withstand abuse in a military environment. So you can shoot bullets through it, you can put it in fires, you can set bombs off next to it, drop it from 12-meter heights, onto concrete, all these tests that you have to go through. And it does very, very well. I'm not a great fan of our American cousins, and we used to get frequently we would get invitations to bid for missile motors from the US, and they always had a requirement in for the insensitive munitions, for the things I was just describing. And invariably, we were the only people who could do it. The US technology would not meet the requirement, and every single time they would change the requirement, and it would go to an American supplier. So the first draft of the requirement, we were the only people in the world who could do it, but they wouldn't let us. Pretending to go out for open competition, but not.
The problem, one of the problems with the strip laminate casings are that they are expensive. So they're very good, they're very safe, but because of the expense, puts the cost of the missile up, we don't sell them. It depends how much you value your defence forces. And we value our people.
Oh, yes.
It might be suggested that other countries don't.
Yeah.
Just a word on where the 18-inch motor, the strip welding, that came from. The early Skylarks were based, the Raven motors and such were based on a thing called Smoky Joe. Smoky Joe was developed for, it was the sustainer for Sea Slug, or no, not Sea Slug, Thunderbird, very early air defense missile. And it was a relatively short length, and it was a wrap and welded, so a sheet of steel wrapped around, welded. And when Westcott was tasked to build the motors for Skylark, they took a number of Smoky Joes and welded them end to end to make up a much longer rocket motor. But as Ian said, there were slight problems with roundness and mass distribution issues. So BAJ then came up with the long strip, which is helically wound and then helically welded. So that's where that came from.
It's quite an interesting technique, and they were doing it when I was there. As the feedstock goes onto the roller, onto the mandrel, which is just a short mandrel, and the welding is all completely automatic. And as it just winds past it, the welding head stays still, and it just continuously welds it. And they have a TV camera inside the machine, so you can see it, actually the welding happening through to check it. But as I said, you end up with miles of weld to grind down into X-ray, and it was never really a particularly popular technique.
As a production engineer, which is what I trained as originally, I have to say that the guys at BAJ were pretty good. They were very good at engineering. They did some wonderful stuff. Any more questions, guys?
Well, if one wanted to use Open Rocket to simulate something like the technical committee's SL, a small launch vehicle, firstly, can you cope with the fact that in a liquid-fueled rocket, CG will shift sort of continually, and more so than with a relatively small solid fuel motor? And I suppose you just have to count the entire stage as the motor, as you've done with no casing to it, no body tube.
Yeah, I think so. The CG shift is calculated, I think, based on a mean density of the motor.
Okay.
I think.
Yeah.
So there is an override for C of G, but I think it's only the starting figure. You know, when I did the override on mass, there was an override on CFG as well. I don't know. It's not something I've ever tried to do. Have a play.
Okay. Okay. Well, that's.
Okay, gentlemen, ladies, are there any more questions?
Yeah, can I just add a comment, really? I loved Open Rocket when it first came out. I was chatting to the guy that wrote it. The trouble is that since then it's become open source, and every programmers keep adding bits, and they don't document what they're adding. So as a professional sim engineer, I'm slightly appalled at that. I don't know how accurate it is, because it seems to be pretty accurate, but until they start documenting their code properly, I get concerned.
Yeah. Have a look at the other program I mentioned, RAS Aero 2. And I think you can use the two of them together. They do the design in Open Rocket because it's got a much better design interface, and then export it in RockSim format and import that into RAS Aero 2. That's also another free program. I think it's got a much better aerodynamic model. and it certainly's got more options in there.
Yeah. Oh, one last thing, Ian. Could I have a copy of your last engine file, the 5, just so I can have a play around with it in my own sims?
Yeah, you should. Bob, did you send those out?
Yes, it should be in the Dropbox. I'll just double check.
I put a pack of about, I don't know, half a dozen motors together, which Bob's distributed. So, but do bear in mind, these are not real motors. They're just generated by an algorithm.
Oh, of course, they're generic, but it's just that it would be handy to debug some on my own sims.
Well, yeah.
Right.
And you can create your own file very easily. I mean, I created those files. If you do a quick search on Google for the format of a RASP file, RASP file, you'll find documents telling you precisely what format it has to be, and then you can just generate the file. And I just wrote a little program to do that, and just let it chug your way through lots of different options.
Mm-hmm.
There is a link on the joining email to download all of the files.
Oh, excellent! Thank you.
There should also be in that link the two models that we went through today, the single stage one and the double stage one, 2-stage one. I think that you should have Open Rocket files for those.
Thanks.
Just bear in mind when you look at the models that rocket motors with high boost, a single rocket motor with a high boost and then a low long sustain do have some design issues. They can be tricky, as Ian and I know.
Yeah,
I don't think anyone would try to do it single stage.
that was the purpose of doing that for the demonstration, was just to try and make the point that in a simple model, to try and demonstrate that it's important where you burn your propellant and the air density where you do it at. It's not that easy. There's no sort of simple way that I know of that you can actually come and see what the best solution is. You just have to do lots and lots of modeling, draw lots of graphs.
Where's the is there a key as to what coloured line on that graph means something? I've noticed that red is altitude, but the other colour.
Yeah, there was a key at the bottom.
Oh, right.
Of the graph. It might not have been on the screen. Again, having said I'm using 2 computers and 4 screens for this, I've also changed the resolution of my screens so that you get bigger images on yours, because I'm working off a very high resolution screen. But because I've come to a low res, I set it a low res, you're only getting part of it. It's chopping bits off.
That was my fault. When we did the run through, I was viewing it on a laptop and I was struggling to actually see what you were doing.
Yeah, well,
I made them change the
not an
screen.
issue. But yeah, have a look at the run it and you see it yourself. Yeah, it tells you that there is a legend on it, and you can plot almost anything you want against anything you want. There's a huge number of options in there.
Any more?
No, just fine.
Does anybody want to go through a sort of tutor demo with Ian? Is it, or have you all had enough?
Oh, it's fascinating, but I was about to say I'll play by myself, but that could be construed.
Not on screen, please.
By yourself is okay. With yourself is not.
Well, thank you very much, Ian, and thank you very much, all the rest of you. I hope you've enjoyed it, and if you've got further questions, you can always send them in to us, and we'll pass them on to Ian. And of course, we have future talks coming up, so keep an eye on Facebook and on the BIS website for more West Midlands extravaganzas. Thanks very much, guys.
Okay.
Excellent. Thank you very much indeed, Ian.
You're welcome.
Thanks to you guys for organising it.
Yeah,
Well done. Thank you.
Thanks,
Thank you.
Bye-bye.
Thanks, everyone.
Bye.